Okay, so this lecture is going to look at change of basis. We've already seen a little bit of this. We've seen a change of basis from the standard basis to and from another basis. Now we're going to say, well, what happens if you have two bases in the mix? Okay, so to start off with, we have a basis for our vector space V, and we have some x in V. We've already seen how to find the coordinates of x relative to the basis B. And we've also seen this equation, that x is equal to this matrix PB times the coordinates. This is from an earlier lesson. But we know that a basis is not unique, that for a vector space, you can come up with many different bases. So what happens if we have a different matrix? Well, for that vector x, we can also find xc and pc in the same way. So now we know how to go from xb back to x. We know how to go from xc back to x. But what if we want to do this in one step? What if we have xb and we want to find xc? So we have the coordinates in one basis, and we want to find the coordinates in a second basis. So what we need to find is this matrix P, which goes from B to C. Remember, PB tells us how to go from the coordinates in B to the standard basis, the coordinates in the standard basis. But now we want to go from the coordinates in a basis B into the coordinates in a basis C. How can we do that? Well, a little bit of algebra tells us how to do it. So we have this equation that x is equal to PB times the coordinates relative to B. We also have the same thing with C. So take the equation for C, flip this PC over to the other side. So we get PC inverse times x times the coordinates in the standard basis is equal to the coordinates in the C basis. But x, we have an equation for x using the B basis. So plug that in. So put that in place of x. Now remember, PC inverse is just a matrix, PB is just a matrix, XB is a vector, so we can regroup things and we can put those two matrices together. And what do we have now? We have that this matrix, which is the product of two matrices that we know, transforms the coordinates in terms of the basis B into the coordinates in terms of basis C. So the matrix we're looking for is simply equal to PC inverse times PB. And it transforms you from coordinates in one basis to coordinates in another basis. Now, take a look at this. PB, or P of from B to C, which is what we just calculated. Recall that PC inverse is what transforms a vector in the standard coordinates into a vector in the C coordinates. That's using the equation PC inverse times x is the coordinates in x relative to C. But what is PB? So PB, if you remember how we built that from an earlier lesson, you just take your basis vectors and stick them all together in a matrix. So PB is simply equal to the column B1, the second column is B2, and so on until the nth column is Bn. So it's just all of your basis vectors in a column, one in each column. So you take P of CB really what that is equal to is translating every basis vector of B into the coordinates, into the C coordinates. Because what is the basis vector? The basis vector is the coordinates, or is a set of coordinates in the standard matrix. PC converts it into, or PC inverse converts it into the C coordinates. So the matrix that converts from B to C is equal to PC times B1, sorry, PC inverse times B1, PC inverse times B2, and so on, PC inverse times Bn. So what you're doing is you're taking every individual basis element in B, converting it into the coordinates of that element in the C basis. That's what this is doing. This leads to theorem 15, which is just summarizing what we just went through. So if we have two bases, a B and a C, it says that there is a unique matrix that will transform your coordinates in B into your coordinates in C. And what is that matrix? That matrix is where every column of the matrix are the coordinates of your basis elements in C. So here's an example. Take R2. So we have a basis of R2 and a second basis of R2. If we have a point where the coordinates are of that vector in C is 3, 3. Find the coordinates in the other basis. How do we do it? Well, what do we know? We know that x equals PB VB, and we know what PB is. We know that x is also equal to PC of the coordinates in C, where PC is that. This should be V's, not X's. So we also know the coordinates of our vector in terms of C, in relation to C. But V is equal to both of those things, so just make them equal. So we have that PB, which we know is equal to coordinates in relation to B, or times that, is equal to PC, which we know, times the coordinates in the basis C, which we know. There's only one unknown in here. So you can rewrite it that the coordinates that you're looking for is PB inverse times PC times the coordinates in C, which is that matrix P, which transforms from C to B, times the coordinates we know. Well, continuing on with that solution, that's PB. So you can do a quick calculation using Cramer's rule or any other method to get the inverse. You can get the inverse of PB. Now we're looking for the matrix that translates coordinates in C into coordinates in B. You just multiply and you come up with that. Now you have the coordinates in C, you want to translate into coordinates in B. There we go. And how do we know this is right? Well, calculate. V equal to PC times the coordinates of our vector V in C, and calculate the P of B times the coordinates in B. If you do that, you'll find out that both of those come to the same thing. So this is shifting from coordinates in one basis to another basis without having to go through your standard basis first.